So now it is recorded. Okay, so thanks for coming. The title is Anti-Ramsey Results for X plus Y equals Z to the K in ZP. Okay, thank you.
Yeah, so as Kate said, this was joint work during the Fairfield University RU, along with our mentors Janar Berkoza, Blanco, Lehman, and O'Cotter. And I'm Ben Lanos. The first thing I want to talk about is a bit of background in Ramsey theory. First, to recall the standard definition of the Ramsey number, just RK for now, which is the smallest number of vertices, so that if I give you a palette of two colors to color the edges of the complete graph, you're guaranteed to draw a monochromatic clique, specifically of size k. We also have the definition on the screen, which is the hypergraph Ramsey number, which is the smallest size of a base set to guarantee that every Q coloring of the R tuples of the base set contains a monochromatic set of size k, in the sense that all R tuples will be the same color. And the reason I want to bring these definitions up at the beginning, even though we're not necessarily going to be using them, is that throughout the talk, I want you to keep these definitions in mind to be able to compare and contrast them with the definitions that we'll make in anti-Ramsey theory. And really, the overarching lesson here is that Ramsey theory is concerned with the existence of large monochromatic structures in huge systems. And so the motto is complete disorder is impossible. Here's a well-known example. Schur's theorem is often taught to undergraduates in a first combinatorics class. And it's basically saying that no matter how I color the natural numbers using a palette of Q colors, I'll be able to find this monochromatic triple x, y, z such that it satisfies Schur's equation, which is x plus y equals z. Well, why is this important for our talk? It's basically because the proof sketch is as follows. Reduced to the Ramsey theory case by taking n to be the Ramsey number, which will guarantee the existence of a triangle when using a monochromatic triangle when using Q colors. And the reason we want to do this is because after we define an auxiliary edge coloring on the edges of the complete graph kn plus 1, we essentially just need to apply the definition of the Ramsey number in order to find this monochromatic triple xyz that we're looking for. And the reason I wanted to highlight this is because this shows that in some sense, searching for monochromatic solutions to an equation, so for example, in Schur's theorem, we're searching for monochromatic solutions to Schur's equation, is really at heart a Ramsey type problem. And the question that I want to pose is, well, is the same true for rainbow solutions? What if instead of a monochromatic triple xyz, we want to find a rainbow triple xyz, satisfying Schur's equation, so that x, y, and z are colored pairwise distinctly? In order to answer this question, I'll need to give a bit of background. First, we say that an R coloring of some appropriate set X is exact if the coloring is surjective. So rather than bracket R, we often think about this coloring like C, like this coloring C, which colors Z8 using red, green, blue, and yellow. We tend to think about it in terms of actual colors rather than bracket R. And a common object that we wish to study is rainbow solutions to certain equations. So in this example, you might notice that 2 plus 4 equals 6 is a rainbow solution to Schur's equation because 2, 4, and 6 all get different colors. You might notice some more things about this coloring. I actually had to edit this coloring. 6 used to be colored green, in which case you might immediately notice that the coloring is in some sense symmetric around 4. And 4 is an important number here because it's equal to p plus 1 over 2. You might also notice that 0 is colored its own color. And these sort of motifs are going to keep showing up throughout the talk. So I wanted to introduce them in this small example. I also want to briefly define what do we mean by color classes. So color classes are going to be very important for the proof of our upward bound that Kate will show you. And basically, it's just the preimages of the colors. So in this example, the red color class just contains the element 0, because this is the only element of Z8 that's colored red here. And similarly for the other color classes. So now we can sort of make like a Ramsey theoretic definition, which is that given a set X, which for our purposes will be like ZP or ZN or bracket N and some equation, the rainbow number of that set and that equation is the smallest positive integer R, such that every R coloring of X has a rainbow solution to the equation. So hopefully you can already see like that we're starting to draw parallels between this definition and the Ramsey theoretic definitions. To give a few examples of like what's been going on in the literature, as you can see, we've selected three from dozens and dozens and dozens of papers that people have written on the subject. It started all the way back in the 20th century when in 1987, Alexei Vintsovchev proved that every equinumerous three coloring of bracket 3n contains a rainbow solution to Schur's equation. By equinumerous here, we simply mean that the color classes all have the same size. So this is definitely one sort of avenue of research that people have done. Another avenue is to study the rainbow number. So this is what Unich et al. Did in 2003 when they studied the rainbow number for three-term arithmetic progressions, which are encoded by the equation x1 plus x2 is 2x3. Since the solutions will give you the three-term arithmetic progression. And lastly, our mentor, Gennard Berkers and collaborators in 2020 studied the rainbow number of the side-on equation, which is x1 plus x2 is 3x4, in both bracket n and Zn. And specifically in this last item, I want to emphasize that these equations are often not only interesting objects of study in their own right, but there's often some applications. So for example, additive combinatorialists or analytic number theorists are often concerned with the side-on equation because it's a good way of measuring like the additive energy of a set. More recently, in 2009, Jean started studying the nonlinear equation x minus y equals z squared. And specifically, he used some density arguments to do with the positive integers in order to find rainbow solutions in any three coloring of the set. Later in 2024, Ansaldi et al. Generalized these results to x minus y equals z to the k for an arbitrary positive integer power k. And they also determined the rainbow number of this equation in ZP. So naturally, our question was, well, if x minus y equals z squared is so well understood, what about x plus y equals z squared? And for that matter, what about x plus y equals z to the k? The intuition for why this is like a substantively different problem is that working with differences that are quadratic residues is often quite forgiving. So for example, the Paley graph is a common object of study, and it has vertex set zq for certain primes q, and xy is an edge if and only if x minus y is a quadratic residue in zq. This graph has all sorts of nice combinatorial and number theoretic properties. For example, it happens to be a strongly regular graph. However, when we throw out the assumption that differences are quadratic residues, for example, by changing the minus sign to a plus sign as we did, quality of life kind of goes down. And so hopefully I'll be able to explain like why this might be the case. So one of the hallmark results of Ansaldi et al. Back in 2024 was that they determined that the rainbow number of ZP in the equation x minus y equals z to the k is either 3 or 4, depending on the prime factorizations of k and p minus 1. So to give a concrete example of this, when k equals 2, this condition becomes equivalent to asking whether p is a Fermat prime, which is a prime of the form 2 to the 2 to the n plus 1 for a non-negative integer n. The intuition for why this might be true is based on something that I'll introduce on the next slide, which is the notion of a functional digraph. Essentially, the number theoretic properties of Fermat primes create a unique structure in this functional digraph. And it happens that the number of components of this digraph depends on the power of 2 dividing p minus 1. And lastly, you can show that the number of components of the digraph is intimately related to the possible rainbow-free colorings. So what is this object that I'm talking about? Well, this is the functional digraph f of x equals x squared. So to give a general definition, a functional digraph is, for example, in ZP, is a directed graph where the vertex set are the elements of ZP, and arrows point from x to f of x. So in this example below, the base set is Z37, and for example, there's an arrow from 0 to 0. There's a self loop because 0 squared is 0. And there would also be an edge from 2 to 4 or 3 to 9, so on. Therefore, if I give you a rainbow-free 3 coloring of Ansaldi et al.'s equation, x minus y equals e squared, or Jean's equation, this will correspond to a vertex coloring of this functional digraph. And it turns out that the colorings of this functional digraph have some very nice properties. The first one is that in some sense, all rainbow-free 3 colorings are completely determined by the color that you give to each component. And this is because each component has to be colored monochromatically. The way that you can see this is that first you might show that 0 has to be in its own color class, like in the example on the third slide. The next thing that you can observe is that because the functional digraph maps x to x squared, for any x in ZP, x and minus x will be living in the same component since they square to the same thing. Through a combination of these two results and a little bit more work, you can show that for any rainbow-free 3 coloring for this equation in ZP, the components of the functional digraph will be monochromatic. So now we're ready to understand Ansaldi et al.'s result, which is why is the rainbow number for their equation equal to 3 when P is a Fermat prime? And it essentially boils down to this proposition. This proposition comes from a paper referenced by Ansaldi et al. And the proposition is basically the culmination of this quite long and technical paper. And it says that for a given prime P, we want to write this prime in the form 2 to the W times Q plus 1. So essentially, we want to extract all of the 2's from P minus 1 until Q and 2 are coprime. And it says that the number of cycles in the functional digraph, f of x equals x squared, is given by this expression. And I also want to highlight that the number of cycles in the functional digraph will be equal to the number of components, because you can show that each component will have exactly 1 cycle, including the component with 0 because it has a self loop. And something that I forgot to mention on this slide is that this is a very rich object of study in number theory, for the reason that pretty much every property of this functional digraph is related to some number theoretic property of P or P minus 1. For example, the sizes of the cycles that you see. You might also notice that there's a complete binary tree coming off of each of the vertices of the cycle. You can compute the depth of this complete binary tree and all sorts of neat results. It's a very rich object of study in this way. So what does this expression mean? Well, first I should clarify that phi here is just Euler's totient function, and x of d is determined by 2 to the x minus 1, which is the smallest Mersenne number divisible by d. Recall that a Mersenne number is of the form 2 to the k minus 1 for k a positive integer. To give a concrete example of this, suppose that my prime modulus is actually from all prime, so it has the form 2 to the n plus 1. When I write it in the form prescribed by the proposition, I find that q is 1. Therefore, in the sum, we only need to consider d equals 1, for which phi of d is 1, either by definition or by taking the empty product. And x of d is 1, because the Mersenne number 2 to the power of 1 minus 1 is divisible by 1. Therefore, the corresponding digraph for this Fermat prime will have exactly 2 components. And to give some intuition about why this forces the rainbow number to be 3, recall that the components of the digraph have to be colored monochromatically. So we only have 2 components. We're going to color 0 red without loss of generality. And then we only have 1 color left over to color the remaining component. So in some sense, there's no more room for a third color. And this is sort of a high-level intuition for why the rainbow number might be 3 in this case. So really the main conjecture of Ansaldi et al. That motivated our research project was that they conjectured that the rainbow number for the equation with the minus sign is equal to the rainbow number for the equation with the plus sign for all positive integers k. So at first the problem didn't seem very interesting. However, we were able to disprove this. And in fact, if you choose k to be p minus 1 and you take p to be sufficiently large, It doesn't need to be terribly large. I think as long as P is at least 7, you're fine. Then the rainbow numbers are different. And in fact, the rainbow number for the equation with the plus sign will be bigger. And so something that I'll quantify on the next slide is exactly how much bigger. I guess it's also important to note that the choice of k equals p minus 1 is not the only choice for which the rainbow numbers will differ in ZP. And in fact, it's an active, it's an area that we're actively working on in order to categorize and classify all of these counterexamples. But this is to say that there isn't sort of a neat pattern of counterexample to their conjecture. It's a little bit messier. So this brings us to one of our first results, which was that the rainbow number for the equation x plus y equals z to the k in ZP is unbounded for certain values of k. So in particular, suppose k is p minus 1. Then choose a prime that's large enough to be interesting, which in our case is at least 7. Then it's possible to show that this rainbow number is equal to this increasing
Question.
expression involving p. Yes.
Actually, I'm confused. So you go back to the previous slide.
Mhm.
So x minus y and then x plus y, right? So the equation is in ZP. So can you just take y to be p minus y?
Yes, and in fact, this is something that Kate is going to talk about in her slides. There is a correspondence between like rainbow solutions to x minus y and rainbow solutions to x plus y.
Okay, all right. Then I will be patient.
So how do we prove this theorem? Sort of to draw a comparison with Ramsey theory, we'll show the lower bound by constructing a certain generic coloring that works for all p, and we'll show that this coloring is rainbow free. This isn't terribly hard to do. As Kate will talk about, we had the assistance of a SAT solver to sort of generate rainbow-free colorings for us, and we were able to kind of see these patterns at a large scale. And once you see the pattern, it's not terribly difficult to figure out what the coloring should be. In order to show the upper bound of this equality, we proceed by contradiction. So this means we'll suppose that we have a rainbow-free coloring C, and suppose that C is using the number of colors on the right-hand side of the equation. Then it's possible to show that C must satisfy the symmetry condition, which is that the color of I has to be equal to the color of P plus 1 minus I for all I up to P plus 1 over 2. And this is really just a fancy way of saying that the coloring must be symmetric around P plus 1 over 2. It's also possible to show that the color of 0 has to be the same as the color of 1, and this color has to be dominating. Now, I'm going to briefly define what it means for a color to be dominating, but you'll notice that this concept really doesn't appear in the rest of our talk. And this is because a dominating color is kind of a tool in the literature that only exists for linear equations. So, for example, our mentors and our Berkers and collaborators, when they studied the Sidon equation, made extensive use of the fact that there exists a dominating color. And this proof also uses it for the following reason. Well, first, let me define it. Suppose you have two consecutive elements of ZP, like 3 and 4. Then we say that a color, like red, is dominating if the following happens. Either 3 and 4 get the same color, or red is one of their colors. And this turns out to be a very useful property to prove all sorts of things about colorings of linear equations. However, as Kate will talk about, this goes out the window as soon as we move into the nonlinear regime. However, in the case when k equals p minus 1, as it does here, you'll know you know that z to the p minus 1 will always evaluate to 1 in ZP, provided that z is not 0. So this kind of turns our nonlinear equation into a linear equation, which allows us to recover dominance and use it to prove the upper bound. So finally, it turns out that these restrictions are enough to guarantee that adding one more color will result in a contradiction, thereby proving the upper bound.
All right, and I'm going to be talking a bit more about the special case where k is equal to 2. So we're studying the equation x plus y equals z squared specifically. And there's a couple of reasons why we're focusing on this one so much. Part of it is that the property of the squares in the group of units of ZP has a really nice cardinality or consistent cardinality and other traits for all odd primes. And we don't care about p is equal to 2 because there's no way to have a rainbow solution there. We'd need 3 terms to have distinct terms and colors to have a rainbow solution, but Z2 only has 2 elements, so it's never going to happen. So for odd primes, 2 obviously divides p minus 1, which means that we have this nice case where the cardinality of the squares in the group of units is p minus 1 over 2. Every square has 2 square roots, and this is something that does not generalize for higher values of k. For example, if k is equal to 3, if 3 divides p minus 1, we have a similar situation where a third of the elements of the group of units are perfect cubes. Each one of those has 3 distinct cube roots. But if 3 does not divide p minus 1, then things are more complicated or well, mostly it's just the case that every element of the group of units is a perfect cube and has exactly 1 distinct cube root. So that already breaks the problem into a bunch of different cases. And to keep things simple, we're focusing on the squares first. And another nice property is that we roughly know how the squares are distributed depending on p. If p is equivalent to 1 mod 4, then that means that the squares are pairs of additive inverses. And if p is equal to 3 mod 4, that means that the squares are exactly 1 per each additive inverse pair. And you can see this through quadratic reciprocity, for example. And that's one of the other results that we find useful in working with this equation in terms of classifying the rainbow-free colorings. There's just more written about quadratic residues than cubic and quartics because they are less nice to work with. And also, quadratic functional digraphs have been studied a lot more than other powers. There have been some things written about other powers, but for squaring specifically, we use resources from Blanton et al., Vasca and Shalit, and Rogers. And also part of the reason why we're starting with k is equal to 2 is because of similar work with the nonlinear counterpart with subtraction. Jean started with characterizing x minus y equals z squared, and then Insaldi et al. Built on it later to produce their results. And even though we cannot use the same technique that they used to generalize their results, because slight addendum to what was said earlier, there is a dominating color for the nonlinear equation x minus y equals z squared, and they used that to generalize their results and come up with a lot of their results. We cannot do that, so we need to come up with new techniques, but we hope that starting with the k equals 2 squared, or k equals 2 case, is going to help us generalize to higher powers of k as well. Okay, so what are our results? Well, in the subtraction case, all the rainbow-free colorings must be symmetric. That is, the color of x is the same as the color of minus x for every single x in ZP. This is because 0 is in its own color class, and each component is monochromatic, and x and minus x are always in the same component of the functional digraph. And so, because all these colorings are symmetric, like Professor Chang said, that means that any rainbow-free coloring of x minus y equals z squared, or of ZP under that equation, will give us a rainbow-free coloring of ZP under x plus y equals z squared, because x plus y equals z squared is the same as x minus negative y is equal to z squared. And so if x, y, z is a solution triple for x minus y equals z squared, then x negative y, z is a solution triple for x plus y equals z squared. And if that's the case, and the color of y is the same as the color of minus y, then there's a correspondence between them, and one of them is a rainbow solution if and only if the other one is. Okay, but if that was all the changes that happened, that would be pretty boring. Changing the subtraction to addition means that we actually had some asymmetry introduced into the rainbow-free colorings. And by that I mean there's some x such that the color of x is not the same as the color of minus x. And because we cannot use any of the techniques that everyone else did for basically every single result that we've been able to find in the literature about Rainbow-Ramsey results, they use the existence of a dominating color. We cannot do that. But what we have that the other nonlinear equation does not have is asymmetry. And we got our results by classifying the asymmetry and putting restrictions on it. And so the results that we got are the existence of rainbow-free three colorings in ZP for P not a Fermat prime. And also, we characterize the structure of rainbow-free three colorings not completely, but we have some lemmas about where asymmetry can occur and cannot occur, and certain results about what color specific elements have to be given an asymmetry. And actually, using the characterization, we found that the upper bound of the rainbow number for ZP in our equation is less than or equal to 4. And so the existence of rainbow-free three colorings on its own is not particularly difficult. It follows immediately from the subtraction case. But the point of saying that is that it gives us a lower bound of the rainbow number. It tells us the rainbow number is greater than 3. Because recall that the rainbow number is the smallest integer, such that any coloring using that many colors has a rainbow solution. So there are 3 colorings without a rainbow solution. That gives us a lower bound. And for an upper bound times P, the lower bound is 3. And we've proved this upper bound for all P. So it's greater than 3, it's less than or equal to 4. That means it has to be equal to 4. Okay, yeah, and as I said earlier, the rainbow-free three colorings of ZP under the subtraction equation is a subset of the rainbow-free three colorings that we have, and the ones that we have that are distinct from theirs are asymmetric. And I do want to clarify that it's not the case that every single prime P has ZP, rainbow-free three colorings of ZP that are not seen in x minus y equals z squared. Sometimes these sets of rainbow-free three colorings are equal, but we do have families of solutions that are different. And so one of the main things that helped us find these were SAT solvers. Because just trying to find existence of different types of solutions under our equation is very difficult if you don't know what you're working with, especially if you try to generalize to larger primes right away. But the tool that we used, at first we used brute force computer programs, which just generated every single rainbow-free three coloring by going through every single coloring and making sure that it wasn't rainbow-free, or that it was rainbow-free. That starts getting slow around p equals 23, so it's not very good for generalizing large patterns. But thanks to our graduate student, Nick Lehman, he could reduce the problem of, is this a rainbow-free three coloring to a Boolean formula, which is a formula that has a bunch of variables that are joined together with conjunction, disjunction, and negation, so the logical operators. And what a SAT solver, a satisfiability solver does, it's a computer program that checks the variables, and if there's some way of assigning true and false to the variables, such that the whole formula is true, then it says it's satisfiable. And it can even tell us what the values you should assign to each variable to make it satisfiable. And if it's not, then it's unsatisfiable and we don't get any information than that. And for our problem, using the SAT solvers, if there is a rainbow-free three coloring, that corresponds to the SAT solver saying the formula is satisfiable, and it can tell us what the specific coloring is. And so this is great because SAT solvers are deterministic in the sense that if you tell it to generate every single rainbow-free three coloring, it will do that. And you can be sure that that's all of them, and there are no more. And so that changes the question from coming up with potential examples of rainbow-free three colorings that are asymmetric, just from scratch, to a question of describing what we see the computer output because we can be sure that that's all the rainbow-free three colorings that exist. And that's much easier. And using that, we discovered these two families of different types of asymmetric solutions. One of them is where everything is red, and for future reference, we usually say that the color of 0 is red because we're going in RGB order. And we have one element that's green, one element that's blue. And so x and y turn out to be the solutions to the system of equations. And this is a pretty natural system of equations to come up with because if you only have one green and one blue element, you know that y can play the role of c, and x can be one of the things that you're summing. So you could have x plus something is equal to y squared. And if the third thing is not x or y, then you get a rainbow solution. And so that combined with the fact that you can have y plus something is equal to x squared tells you that you have to have x plus x is equal to y squared, and y plus y is equal to x squared. And another thing is that we want x plus y to not be a square, because if it is, then we have a third z that's distinct from x and y. X, y, z would be a solution triple, and that would also be a rainbow solution. And solving this system of equations gets that x and y are the primitive cube roots of 8. And, or to be clear, x and y could also be 2, but that would mean that x is equal to y is equal to 2, and we don't want that. We want them to be distinct. And that means x plus y is equal to negative 2. So the fact that primitive cube roots of 8 exist happens when 3 divides p minus 1. And the fact that x plus y is equal to negative 2 is not a square, that gives you a condition on p mod 8, and combining them, we get this restriction p is equivalent to 7 or 13 mod 24. That's where that comes from. And then we also have these two outliers with one green element, one or 3 blue elements, and the rest red. This only happens when p is equal to 11 or 23. This is a solution to a more complicated system of equations. I don't think we would be able to get this if we did not have the colorings generated by the sat solver, because the way that this system of equations was conceptualized was by observing what we were seeing from the computer and solving it. And by solving it, you get that the only cases where the system of equation holds is when p is equal to 11 or 23. And now, these are all the ones we found. We think it's all of them because with the stat solver, we could generate, I believe, up to around primes up to 500 about, until it starts getting really slow. And it's possible that there's some p such that there's a different system of equations that that prime satisfies and gives us another asymmetric rainbow-free coloring, but we're not sure, and we think this is all of them. Okay, and the upper bound was one of our more substantial results because it led us to the rainbow number directly for non-Fermat primes. And because every single other result in the literature has used the existence of a dominating color for the upper bound, they had more complicated lemmas building up to it as well, but every single one of those lemmas used the fact that there was a dominating color as a given. We can't do that. But the one thing that we do have over the other nonlinear equation that was studied is the asymmetry, and again, we're going to make full use of that to make sure that we can get somewhere. And it turns out that the asymmetry is really constrained. This equation does not want to give you asymmetric rainbow-free 3 colorings, but when they do exist, you have some really nice properties about them that we've been able to figure out. Okay, and this lemma is about the color of minus x and the color of x squared. We use this result so much that we kind of take it for granted, but I figured it would be good to specifically mention it so it's not confusing later on. So again, we're assuming the color of 0 is red, and that means that if the color of x is already defined, the color of minus x is either red or the color of x, and similarly, the color of x squared is also either red or the color of x. And the proof for this is quite simple because x minus x and 0 is a solution triple from this equation. And since x and 0 are already defined, you cannot have minus x be a distinct color from the other two, or that would be a rainbow solution. So either it's equal to the color of x or the color of 0, which in this case is red. And you observe the same thing with the solution triple x squared, 0, and x. And also, as an aside, this is also a solution triple for the subtraction equation. And so we get a similar result to them about specific locations on the digraph. And so since x squared, 0, and x is a solution triple, and the color of 0 and x are already defined, the color of x squared has to be one of them. And specifically in the rest of our results, we care more about the color of minus x, although the color of x squared does come up. And so when the color of x is not equal to the color of minus x, we see that x is asymmetric as shorthand. This is with regards to a specific coloring, but for all of these results, we're going to be speaking with a coloring that is fixed, and so we can assume that we're always referring to the same coloring. And when we say x is asymmetric if and only if minus x is asymmetric, right? But we're only going to be focusing mostly for these results on the case where the color of x is not red, so the color of minus x is the one that's red. Okay. And this is another really, really important result that we've shown. So if x is green under this coloring and it's asymmetric, so minus x is red, and there's some y such that y is a different color, so that means that we have at least a 3 coloring, maybe more colors, this generalizes, then the color of x squared minus y is equal to the color of y. And the proof for this is, again, by constructing solution triples. X squared minus y plus y is equal to x squared. And so we have 2 solution triples now because minus x and x are both equal to x squared. And that's also another case where it's nice that we're dealing with an even power of k, because if k is equal to 3, for example, we can't conclude that. So we have x squared minus y, and x squared minus y, and minus x. And if the color of x squared is not, or the color of x squared minus y is not equal to the color of y, where the color of y and the color of x and minus x are already defined, if it's distinct from both of them, it's not red or green, then both S1 and S2 are rainbow solutions. If the color of y is the same as the color of x, then S2 is a rainbow solution. Or sorry, the color of x squared minus y, rather, because the color of y is already defined. And if the color of x squared minus y is the same as the color of minus x, then S1 will be a rainbow solution. So the only way to deal with the situation is for them to be equal. Okay. And these lemmas all build on each other. This one's going to use the previous one quite heavily. And if there is some x that's asymmetric and green, and we have another color class that's distinct from them, then there is some element of that color class that's also asymmetric. And this is important because it tells us that if asymmetry exists, it's, I don't want to say uniform quite yet, but it exists everywhere in every single color class. No color class can have a monopoly on it, I guess. And the proof for this statement is contradiction. Suppose there is a color class where all elements are symmetric, with the color of x being the same as the color of minus x. And first, if C is this color class that's also symmetric, and there's some y in C, then by the previous lemma, x squared minus y is in C, where x is our asymmetric element. And because x squared minus y is in C, and C is symmetric, while the color of minus x squared minus y, which is y minus x squared, is also that same color. And so we apply the lemma again to y minus x squared, and then we get that x squared minus y minus x squared is in C, which is 2x squared minus y. You can repeat this argument to show that kx squared minus y is in C for all natural numbers k. And it turns out that kx squared minus y equals x squared has a solution for k, which means that x squared is in C. And that's going to be a contradiction because x squared has to be either green or red by the previous lemma, or by the first lemma. And the proof uses the fact that ZP is a field because when we're solving x or kx squared minus y equals x squared for k, we are inverting x squared. And x squared is not equal to 0 because 0 is red and x is green. And because ZP is a field, that means that x squared has an inverse. And this is not true for composite as n and Zn. And this is why, as I'll talk about later, we cannot generalize this upper bound result to other places. Okay, and this result says that if an asymmetry exists in the coloring anywhere, then every non-red color class has exactly one asymmetry. You cannot have more than that. The asymmetry is extremely constrained. And the proof of this uses all the previous lemmas as well. So by contradiction, if there is a color class with multiple asymmetric elements, we'll just say 2 for now, then we know that the color class blue, or blue is another color class, has an asymmetric element. And then we can iterate saying that, well, because I is blue, so is x squared minus I, so is y squared minus I. And then x squared minus y squared minus I is also going to be blue because of the second lemma that I discussed. And again, you can iterate this to get that kx squared minus y squared minus I is going to be blue for any natural number k. And this time, if you set that equation equal to 0, you get that 0 has to be in blue. And that's a contradiction because 0 is red. And again, this proof uses the fact that ZP is a field. You're solving for K by inverting elements, inverting x squared. And that's not possible necessarily unless you're in a field. Okay, and this is the lemma that led us to the upper bound. It tells us exactly where the elements of other colors have to be, or at least one. This result is significant because you're dealing with only two colors, a priori. X is green and minus X is red, but this tells you where you have a third color showing up based on just elements that are green and red. And so if X is asymmetric, then P plus 1 over 2 times X squared is blue. And the proof of this is pretty simple because by the previous lemma, every non-red color class has exactly one asymmetry, which means that the cardinality of the color class is odd. This is because all the others are in additive inverse pairs, and then you have one element whose inverse is not blue. So an even number of pairs plus, or even number from pairs plus one odd element is odd. And so we can also partition the color class into these pairs j and x squared minus j. This is just the partition that you get from applying x squared minus j to every single element of the color class, because x squared minus j is equal to j. And so you have this correspondence. But because the cardinality is odd, that means we have to have one element such that j is equal to x squared minus j, or I as I call it here, because otherwise that would mean if all these pairs were distinct, that means that we have an even number of elements because every pair has a distinct number, has two distinct elements. And we want the cardinality of B to be odd, so that can't happen. And x squared minus I equals I has a solution here. We can get that it's equal to P plus 1 over 2 x squared, and that has to be blue as we've constructed here. And from this, we immediately see the upper bound because if Y is a fourth color class for yellow, swapping B for yellow for Y here means that P plus 1 over 2 x squared is in Y as well, but that can't happen because the color classes are a partition of ZP, so it can't have two colors at once. And so this proves an upper bound for every single prime of 4, and this shows that a 4 coloring is impossible. Okay, and with that settled, we have some future directions of what we want to talk about next. The most glaring issue is the question of Fermat primes. We have an upper bound, we have a lower bound of 2. We cannot use the same techniques that Jean and Ansaldi et al. Did about the components of the digraph because their components are monochromatic. Ours do not have to be under the asymmetric colorings. And we want to figure out what the rainbow number for Fermat primes is. We are pretty sure it's 3. I believe that the computer can generate even large Fermat primes quite quickly, all the rainbow-free colorings for that. So I believe we know that there are no 3 colorings for all the known Fermat primes, but obviously that doesn't mean that there's no rainbow-free 3 colorings for all Fermat primes. And we also want to completely characterize the rainbow-free 3 colorings of CP, show that we really have found all of them, and we're not going to encounter more solutions to certain systems of equations later on, and we're probably going to need to continue to study the asymmetry and try to further restrict it to have some more results about that. And we're also interested in the rainbow number of our equation over Zn for our composite n. We have some lower bounds that depend on the prime factorization of n, and by these lower bounds, we know that the rainbow number is unbounded. It's not like the primes where it's either 3 or 4. And we also want to generalize the rainbow number of x plus y equals e to the k, as I mentioned earlier, for ZP, and potentially Zn later, but ZP is definitely the first stage to go in because ZP is a field. And we want to do that for other values of k, like Ansaldi et al. Did as the respective version of their expansion on Jean's work with x minus y equals e squared. And that's it for us. So if anyone has any questions.